Hi, and welcome to a video on geometry brought to you by the Answer series. In this video, we will start looking at circle geometry without bringing in any tangents. Very often, a geometry question can be quite wordy. We need to identify the things that we need to take note of so that we're not overwhelmed by everything we need to read. So we know that angle PQRS is a cyclic quadrilateral. If we trace the quadrilateral, it's much easier to process what they're saying. So that quadrilateral lies on the circle. We've been given QRKW as a parallelogram, which means lots of parallel lines. We know that the lines running this way are parallel. Because they've marked everything off so nicely on the sketch, we would have actually known that even if they had not told us that we had a parallelogram. It's getting very busy, so I will mark the other parallel lines in at a later stage if and when I need them. Make sure that any angles that they've given you are indicated on the sketch, and if they're not, add them in. So angle PST is the same angle here as angle S2. It's the same angle with a different name. And angle Q1 is indicated over there. So all the important information is on the diagram. A checklist is almost like a shopping list. So we are going to think about every question in the same way if we get stuck. So don't give up on a question just because it seems complicated. Analyze it. Ask yourself, what do I need to find or prove or show? Where am I working on the sketch? What do I know that could be helpful? And can I justify my answer? The moment you tackle the question with a concrete approach, having a strategy, it sometimes just feels a whole lot more manageable. All right, so in question 1.1, we need to calculate the size of angle R. So angle R, we're going to take ourselves there on the sketch. We're going to be observant because that's the essence of geometry, always knowing where you are and what you're looking for. Angle R is tucked into these two lines, and so if we trace that along, we get a co-interior shape, a C shape. And based on that, we can conclude very easily that the angle at R is 80 degrees. If we hadn't been successful with the co-interior angles, we would have had other options. So our little think tank, we spit out all the options that relate to parallel lines because there are so many parallel lines. We could have used alternate, corresponding, or co-interior angles. To write that up is fairly uncomplicated. We know that angle R is 80 degrees. We know we have co-interior angles. Commonly, people forget to write the parallel lines in, and they are critical to the proof, and I'm going to explain why. If you have a look at a different set of co-interior angles, there's no doubt that angle P is co-interior to angle S1. But because the lines that form that C shape, QP, is not parallel to RT, the angles formed in that C are not supplementary. So the only way that you're going to earn your marks if you use co-interior, corresponding, or alternate angles is if you make sure that you name the lines that are parallel. In question 1.2, they are asking us to find the size of angle P. So we're going to go to the sketch and locate angle P. We're also going to fill in the last thing that we did in the previous question. And if you do that, you actually don't even have to think too hard because you'll notice that R and P are opposite each other in the cyclic quadrilateral. So without even having to think about the extra things that we could have thought about with our think tank at the bottom, we can see at a glance that angle P must be 100 degrees because the opposite angles in a cyclic quad are supplementary. However, just for future reference, we have a circle without a center, so had it not been so easy to solve this problem, we would have only had 4 things to think about. Could we have found angles in the same segment? Could we use the exterior angle of the cyclic quad? Do we have opposite angles that we can use, which is true in this case? We'll give that a tick. Could we use equal chords? So you do go in with a set of questions that you can answer that will help you solve almost every problem. To write that up is very straightforward. We know P is 100 degrees. Why do we know that? Because we have the opposite angles of a cyclic quad. In question 1.3, we've been asked to work out the size of angle PQW. When we locate that question, it is this little angle here. Now, we're not sure at a glance exactly what we have to do, so our think tank becomes quite useful. We're going to think about this and realize that we have a circle without a center. The line that is parallel is positioned in such a way that Q2 is unlikely to be solved using parallel lines. So we've got some things to think about. Perhaps we should consider the angles in the same segment. If we're going to do that, we need to trace back this angle to the circle. We can see that it's coming off the circle from an invisible chord at PW. But a quick look at that will tell you you don't have angles in the same segment, because if you try to get back to the circle from P, you could come to S, but that's not joined up. If that was drawn in, and if we knew the angle over here, we could have used angles in the same segment. But the way this question has been presented, there's no help coming from that area. So we're going to put a line through our angles in the same segment because they're not going to help us. The next thing to consider would be exterior angle of a cyclic quad. So is there perhaps anything that we can do? And to understand that, we need to first process, do we actually even have an exterior angle? The answer is yes. What we also need to do is think about where is this partner. So the partner is opposite the interior angle. This angle at S1, opposite that is this angle at Q, and that tells us that the 136 degrees that they gave us is equal to angle RQP. That means we've solved our problem, because if angle Q1 is 100 degrees, then the angle Q2 must be 36 degrees. We didn't know anything about chords that were equal. Although we didn't use the opposite angles of the cyclic quad, it is possible that in a different question we might have found this very useful. It is possible that you don't recognize the exterior angle, and if you use more basic work from earlier grades, it's easy to use the straight line. They gave us 136, so we can fill in the 44 ourselves, and that would be a completely different strategy for finding the opposite angle. So in this particular question, we could use either the exterior angle of the cyclic quad or the opposite angles of the cyclic quad. To write that up, you have to make sure that if you used a slightly longer method, that you explain everything that you've done. So the shorter, more efficient method is to go straight to the answer. PQR, this big angle, is 136 degrees, based on the fact that we have an exterior angle in this cyclic quad. PQW is the difference between the two angles positioned, the whole angle that we found, 136 degrees minus the angle that they gave us to start with. So angle PQW is 36 degrees. Alternately, we can actually decide to find S1 first, and that means that we've got an extra step, because we have to explain that S1 is 44 degrees based on the fact that we have angles in a straight line. Then we have to explain that angle PQR is 136 degrees based on the opposite angles of a cyclic quad. So you can use a longer method as long as you justify it. The algebra here is the same, does not have to be shown. PQW is 36 degrees. In question 1.4, we have been asked to find the size of angle U2. It's a very interesting question, because if you have a look at U, it is not positioned on the circle. It is basically in no man's land. Why this is really important is that you cannot use circle theorems if your angle is positioned anywhere other than on the circumference of the circle or at the center. So in the process of finding U, we have to think back to our earlier geometry. We could, in some questions, be required to use angles in a triangle or vertically opposite angles. Basically, in this question, so much is focused on parallel lines that we are probably going to be making use of either alternate or corresponding or co-interior angles. So if we think about the fact that U is positioned on the line QUW, there's no useful information up there. We're going to trace the line, which is a transversal, down to the next parallel line, and then the logical place to go is to the right, because we can see that angle S2 is given as 136 degrees. So to find angle U2, we are simply going to draw on the fact that these angles are alternate and angle U is 136 degrees. We can write up the solution by simply stating what we already know to be true. So angle U2 is 136 degrees, alternate angles. Please remember once again how important it is to include in your reason that QW is parallel to RT. A reminder of why this is so important. If we highlight a different set of alternate angles, the angle at P is described as being alternate to the angle at S2, but those angles are not equal because those lines, QP and RT, are not parallel. If you use alternate, corresponding, or co-interior angles as a reason, you must name the parallel lines. In example 2, we are working with a slightly more complicated sketch because there are two circles involved, and we are working with unknown values because we are working with x's and y's. That doesn't mean the question is difficult. It just means we might need a slightly different approach. So to start with, before you even process the information you've been given, take the time to highlight the circles in different colors so that you can see them clearly and you don't confuse information from one circle to another circle. So there are little strategies that make geometry so much easier to manage, and one of those is using color whenever things get confusing. All right, so if they do refer to those two circles, we are now well equipped to handle any information that they give us. So if we read through the information, we're looking for keywords like tangent, diameter, angles in the same segment, anything that might help us answer the question, but there's really nothing helpful in this text. So we are going to move straight on to the fact that we do know that angle A is equal to x. That's in the information that they're giving us. So we need to process that, and not only process it in terms of we know that it's been given, but we do need to go to the sketch and locate it so that we know what we're working with. So angle A is equal to x, very important. In addition to that, they've also told us that angle R1 is equal to y. So again, we're going to go to the sketch and make sure that we know where that is coming from. Okay, now we are ready to answer the first few questions. So, having a look at question 2.1 specifically, we have to name, giving reasons, another angle equal to x and then another angle equal to y. Okay, I'm going to re-highlight my circles so that I know where they are. So again, we have a circle in blue and a circle in yellow. Now when we handle each question, we will clearly be able to see where we are working. Okay, so angle x, if we go to the sketch, we can pinpoint the fact that we've got a starting point. Now we need to think about our information, and the sketch does not have any center point marked. So as we tackle this question, we are going in with questions that we ask ourselves. So there are only 4 questions if there's a circle without a center, and they are, can we use angles in the same segment? If not, can we use the exterior angle of a cyclic quad? Could we perhaps use the opposite angles of a cyclic quad? And if none of those work, do we have equal chords, in which case we will have equal angles? So we take these one at a time. The trigger as to where you should start always or often comes from the sketch. So I'm going to trace back the angle at x, which is angle A, find out where it's starting, and I can see that a chord is subtending that angle. So now what I need to do is ask myself, is there another angle subtended by that chord? To do that, you go to the endpoints of the chord and you see if you can trace a line onto the circle edge. And then from that point on the circle edge, can you get back to the chord? And yes, you can. So angle B1 is very definitely equal to angle A. And in this particular instance, we are going to make use of angles in the same segment. Okay, now we just need to find another angle equal to y. So what we need to do is make sure that we start with what we're given. So angle R1 is equal to y. We notice that that is related to the circle, but outside the circle. And with outside the circle, it means that we are probably going to be using the exterior angle of a cyclic quad, because this reason is specifically designed for the information that we have been given. We're going to start by highlighting the quad so that we can see it. So if we trace the quad and at the same time continue the line dr to C, we can see clearly now the picture of the exterior angle, and the exterior angle equals the interior opposite angle. So the angle that this R1 relates to is angle B2. it's sometimes difficult to see that. So another trick would be to find the partner angle on the straight line. So you have a straight line. Angle R2 is the partner to angle R1, and the interior opposite angle that you are looking for is the angle at B2 because it is opposite to angle R2. All right, so we can solve both of these problems. We also need to remember that the exterior angle, if we find it difficult to use, we could use a longer method and fill in that this angle on the straight line is 180 minus y. And then we could go to angle B2, and using supplementary angles, we could still come out with a value of y. Just is important that if we use a longer method, we remember to state every reason that is required. So in this case, we would have to state angles on the straight line and opposite angle cyclic quad. When you write up the solution, always choose the shortest option that you have. So angle B1 equal x, there were no other options, angles in same segment, short and sweet. Angle B2 equal to y, if you're able to manage the exterior angle of the cyclic quad, that is by far the easiest way to write the solution up. 2.2 is refreshingly different. We are being asked to prove something, which means we have to think quite hard. And what we need to prove is that SCDB is a cyclic quadrilateral. All right, so the first thing that we need to do is to ask ourselves, can we use what we've done in 2.1? And without knowing whether the answer to that is yes or no, it's always a good method to fill in what you know on the sketch before you start the follow-on questions. The second thing that you definitely need to think about is, if this is a cyclic quad, then what has to be true? There are three theorems that link to the cyclic quad. If you want to prove a cyclic quad, you either have to prove that the opposite angles add up to 180 degrees. So in other words, could we possibly prove that angle B and angle C add up to 180? Or we could prove that the exterior angle, so angle S1, if we're able to prove that angle S1 is equal to the whole of angle D, then we could prove it's a cyclic quad by using the converse exterior angle theorem. Or if we had lines crossing, we could use converse angles in the same segment. All right, that's not an option because we don't have that crossing of diagonals here. So the only options we're going to try, the exterior angle doesn't look promising because we don't know anything about S1 or D. But what we do know is that the whole of angle B is equal to x plus y. So without having any justification, we know that this angle has to be equal to 180 minus x plus y. If it is not, this cannot be a cyclic quad because the angles opposite each other will not add up to 180. We can't say it has this value because it's a cyclic quad, because that would be circular logic. So we know what we need to get, but we cannot get there from the cyclic quad. So what we're going to do is highlight the information that we have and see what we can do differently. And if we think about the angle that we want to focus on in this corner, it is in the same triangle as angle y over here and in the same triangle as angle x. So if we simply draw that triangle in, we can see that angle A and angle R1 and angle C add up to 180 degrees, and that's how we're going to explain our angle. So we get this angle independently of the cyclic quad by using the angle sum of the triangle, and then, because they are positioned opposite each other, we can explain that we have a cyclic quad. All right, so that sounds really complicated because it is, but it's not that difficult to explain. Angle C1 is 180 minus the sum of x and y, and that's simply based on the triangle, which I'm going to highlight for you again. So we know that angle C is 180 minus the sum of x and y. We knew from an earlier question that the angle at B was x plus y. Now what that means, if we highlight this quadrilateral for ourselves, is that we've actually worked out a relationship between the opposite angles. And it's a good relationship because the angle at C is 180 degrees minus the sum of x and y. And the angle that we worked out earlier at B, the combination, if we add those two angles together, we will get 180 degrees. So we can with confidence say that this is a cyclic quad. We're using the converse opposite angles of a cyclic quad. It's risky to not use the word converse. So if you say it's a cyclic quad because the opposite angles add up to 180 degrees, that's great. But if you say it's a cyclic quad because the opposite angles of a cyclic quad add up to 180 degrees, you actually don't get the marks for that reason. So be careful with your reasoning on converse theorems. Okay, so we up to the last question. It is very important when you do a proof to really read it carefully and make sure you know what you're looking for. And also, don't overlook things that might seem obvious. 30 degrees is given, but it's not on the sketch. And 100 degrees is given in this question, but it's also not on the sketch. So before you do anything else, fill in the 30 degrees and spend some time thinking about why they've given that angle, and fill in this combination as 100 degrees. So those angles are given. All right, now, in order to prove a diameter, we have to first understand what a diameter is or what it does. So if we do have a diameter, then the angle here has to be 90 degrees. But if we do not have a diameter, the angle cannot be 90 degrees. Okay, so if we update our sketch, which is neatly done on this page, we can see that in order to use the angle of 30 degrees and the angle of 100 degrees, and there's a very strong possibility we're going to use both because they wouldn't have bothered to give them to us if we didn't need them. What we are trying to do is find the size of x plus y. So it feels a little bit strange to be working away from what we're trying to find, but we have to work with what we know towards what we want to find. Now, by using the angle of 100 degrees and the angle of 30 degrees, we can actually see that angle C is 70 degrees because the exterior angle out here is equal to the sum of the two interior angles of the triangle. The good news is that if you find that difficult, there is another way around that. You do have the right to instead take the 100 degrees, work out that the angle on the straight line with that 100 will form a combination that adds up to 180 degrees. So you could start with the 80 and the 30 that they gave you, add that up to get 110, and from there you can deduce that angle C is 70 using the angle sum of the triangle. Once we've done that, we're almost home and dry. Earlier on we proved that we had a cyclic quad. So we go back to this quad. The opposite angles do add up to 180 degrees, and that means that we are sure that the angle combination of x and y is actually 110 degrees. Now, can we justify it? Okay, and it's surprisingly easy to do in this case. So we're going to start by stating the obvious. Angle SCD is 70 degrees, exterior angle of triangle. Angle SBD, which is directly opposite, is 110 degrees, opposite angle cyclic quad. We make our claim, DS is not a diameter. How can we say that it does not subtend a right angle?
Check out the video description below for practice questions from our study guides. If you found this video useful, give it a like and subscribe to our channel so you don't miss any new episodes. Follow us on Instagram or Facebook to stay on top of the latest TAS news and launches. So that's it for now from the Answer Series, your key to exam success.